4番目の講演は
Moving on to presentation number 4 from Associate Professor Ryo Omura, Keio University, and he's going to talk about hydrates for air conditioning and other. Thank you very much for the kind introduction. I'm Ryo Omura from Keio University. I'm sure that everybody is concerned about the typhoon, but hopefully it will pass while you're listening to the presentation. I think there is a couple of more. I would like to talk about application, new application, including air conditioning. Mostly, I want to talk about how to build air conditioning technology based on hydrate. This summer in Japan, we had to save energy, and I think more people were conscious about how much air conditioning they were using. Hydrate may be able to contribute in this sense. So how did this discussion start? Clathrate hydrate has this physical property which makes it unique. Basically, it's a type of ice. So when it's formed or disassociated, there's a lot of heat associated with this process. So the technology is based on this physical property. For example, the formation and the dissociation heat is about 334 kilojoule per kilogram, which is very high. This is for ice. And depending on the guest property, there's a range for hydrate, but it's only slightly less than ice, about 70% of ice, or depending on the mass or the space, some of the hydrates would have a higher temperature than the ice. So using this physical property, there are two ways we can apply hydrate to air conditioning technology. One is air conditioning, meaning cooling. So this is suitable for thermal storage. We can use the off-peak nighttime power and form hydrate during the night, and which can be dissociated during the day to cool down the buildings. The other way is to form a cycle of forming and disassociating of hydrate. So heat pump, wasting heat or discarding heat from high heat to low heat space. This would be possible. Actually, the thermal storage with using hydrate is not such a new topic. It already has a long history of research. In the 1980s, the research had already started. And guest material, non-water material, included fluorons in the beginning. And due to Montreal Protocol and the Kyoto Protocol, people had to move away from these types of materials. And at the same time, people basically gave up hope on hydrate thermal storage. So that was the tendency in the thermal engineering field. But fluorocarbon is not the only thing that you can use for hydrate. And for example, Dr. Ribmister can give you a proper lecture about which substance would be the best suited ones. And I'm sure there are many more hydrates. One example, Dr. Ebinuma from ICE proposed this, and JFE Engineering commercialized this, tetrabutyl ammonium bromide and water. Another example, which came a little bit later from Keio University and IHI, this was a joint research, cyclopentan used as a guest for hydrate, really suitable for thermal storage. And there may be other hydrates that could be used because we have not really exhausted our search for other candidates. I will talk about this later on. And other than thermal storage, we have the other technology, heat pump, which is a relatively new technology to speak of. Several years ago, TEPCO, IHI Group, came to Professor Mori and suggested that a heat pump could be built based on hydrate technology. So I was working at ICE at the time and provided support and found out that this was quite feasible. And I myself and Professor Mori are still continuing our university level research for this. Today, I would like to talk about heat pump, which is a more complex technology, how it works in principle, and how realistic it is. So, some suggestions about which hydrates to use for the system, and also I would like to talk about the research and initiative going on at the university level to be ready for commercial products. And for thermal storage or cool energy storage, I'm sure that you understand the necessity already. So there is peak and off-peak of electricity usage. That is why storage is effective. And a hydrate suited for thermal storage, what is the most recent research? Now, I would like to start with a brief review of heat pump technology. So this is industrial thermal engineering, a topic that you would study at school, university. This is one of the most difficult things to understand. You may not want to hear this phrase, but this is actually a very important technology. So the principal mechanism of air conditioning is because the cooling cycle is working, but what is happening is basically the coolant is evaporated or expanded in order to remove heat away, and that's how the room becomes cool. And then it's compressed and turned back into liquid. Or during compression, the temperature would increase, so the thermal energy can be discarded to the outside area. So you can cool the cool area and discard the heat in the hotter area. Listening to this, you might think that usually the heat would travel from a high temperature to lower temperature. That's how it works as energy. So that's the second principle of the thermal principle. And you may think this is going against that. But actually, this is the human wisdom. We're just utilizing the natural energy and using the natural energy, meaning we already have heat in the air, in the sea or rivers or underground waters. And by utilizing the energy that's already in nature, we can basically use more thermal energy than the energy that we're putting into the system. Twofold, threefold, fivefold, so on. So whether it's cooling or heating, heat pump should be used because that's efficient. I think that's a long-standing discussion. Hydrate heat pump does not exist yet. So in your daily life, or when you come to this kind of building, what you would see is basically the vapor compression type, or the reverse Rankine cycle. Cooling cycle, which is helping transfer heat from one area to another. So this is the Rankine cycle that you might have learned in the industrial thermal class. And this is what it would look like. So there is some kind of liquid inside the loop, and the pressure of the liquid will be reduced through the expansion valve, and the evaporation would occur. And this means that it would take away heat, cooling down the room, and the evaporated liquid would be compressed and turned back to liquid. Again, it would generate heat in this during condensation, and this heat will discard it to the outside. So this is the reverse Rankine cycle. And the working medium would be fluorocarbon or non-fluorocarbon. Refrigerators would use propane and butane, a mixture of these two, and then heat pump used for cooling and heating would use CO2. So this is the compression heat pump, or the reverse Rankine cycle. Now, the idea is, can we change the working media? Put hydrate and water within the cycle to do exactly the same. This is the principle of hydrate heat pump. So let's say we start with hydrate. Hydrate has to be slurry, otherwise we cannot move it down the cycle. So we have a mixture of a hydrate and water, and this will be moved using slurry pump. It goes through the expansion valve, and then the pressure would go down, take away the heat, and cool down the room. And once hydrate is associated, the guest material is basically gas, and then the rest is water. And then using pump and compressor, you can compress them together again and generate more hydrate. And when the hydrate is formed, again, heat is generated, which can be discarded to the outside environment. So this is basically exactly the same as the reverse Rankine cycle. And heat and the pressure, if you look at the state diagram, high pressure, so at high pressure, high temperature, we generate the hydrate, and then this cycle will be repeated to discard heat in the hot area and continue to cool the cool area of the building. You may think that the vapor concentration method is already good enough, but there are some technical aspects to this. For example, let's say we use 1 mole of guest material and 7 to 10 mole of water. And per mole, the amount of heat generated by hydrate is basically 4 to 8 times as compared to the same amount of, let's say, propane. So if that propane is used for condensation, it's better to mix it with water to form hydrate to increase the efficiency. So if the compressor power is the same, basically it should be 4 to 8 times more powerful. It's not that simple, the whole story, but that's one aspect. And this is a mechanical engineering, very technical, but most of the energy used in heat pump is basically for compressor. So compressor is used to compress the air, which requires a lot of energy. Increasing this efficiency is important as a technology, but in the case of hydrate, there's water as well. So gas and water can be compressed together, so compression efficiency is much better. This is more or less the same as equilibrium temperature compression. So hydrate is basically solids, and the solids are moved by slurry pump. So immediately you might think that it would require more energy. But if you compare it against the compressor that's being used for the traditional air conditioning system, this is smaller by 10-fold or more. So, using hydrate, if you wanted to have a heat pump system, what are the specific challenges? First of all, if you want to cool the room, we need basically to reduce temperature by about 10 degrees, but we have to discard the heat to the outside, so the hydrate has to be, the temperature difference has to be about 30 degrees centigrade. Do we have such hydrate? Yes, we do, and I will explain about that later. So using this type of hydrate heat pump, we can achieve values that was never achievable by conventional air conditioning. So that's our objective. In terms of specific numeric numbers, this is the coefficient of performance. We have an amount of energy that we can use, for example, for cooling, how much thermal energy can we discard, and how much electricity we're using to do that. So let's say we put in 1 unit of energy and cool down something by 5 units, and then the COP would be 5. Well, the conventional air conditioning, even for residential use, is a COP of 5 to 6. So it's really good. If you look at the sticker on your air conditioning system, you might find this number printed on that as well. When it comes to air conditioning for huge buildings or stations, it's close to 7. And what we want to achieve is as high as 7 with hydrate heat pump. So this is dream technology, and we don't know how far we can go, but this is where we would want to aim. What are the challenges of hydrate a heat pump? As I mentioned earlier, if it's just cooling rooms, if you're doing a direct discharge of the heat, basically it has to be about 40 degrees. So it means that the hydrate has to be generated at a very high temperature. But hydrate is a type of ice, as I mentioned. So this is basically a conflict in logic. So are there any hydrates that would exist in high temperature? Is that really realistic? That's the first question. And this is a completely new technology as well. So how do we design the whole system? This is going to be more of a future, long-term challenge. So Keio University and ICE did this joint research, and we have identified several hydrates that can discard heat at 30 degrees. So these are some realistic examples. Not comprehensive, but these are some of the examples. Krypton, it's a rare gas, and a cyclopentane or fluorocyclopentane. These are used as liquid. So these would coexist in the same space, and hydrate can be formed very, very easily from about 10 degrees atmospheric pressure or 30 degrees at 4 megapascals. So this is actually possible as indicated here. So with realistic pressure, it is actually possible to discharge thermal energy into the atmosphere. So last 5 to 6 years, ICE and Keio University have been working together showing this result. But going forward, there are some challenging issues. For example, krypton cyclopentane will have to be mixed, and also there is water as well. And then hydrate is solid as well, meaning that it would involve 4 different phases: gas, liquid, liquid, and solid. So how would they work together? We need to fully understand this multi-phase system to design the heat pump. So there is liquid gas and liquid water, and then there is a gaseous gas in contact, and the hydrate would be formed. What would happen then? So this is exactly what our research team is doing at the moment. And based on the crystalline formation, we know that there are different levels of concentration. So which kind of formation is the best for which type of reactor? So this is the really detailed research that would give some light to this, to the answer to this question. So we are progressing with hydrate heat pump, but we don't believe that we can finish all this within the next few years. So let's see how far we have come so far. First of all, we know that there are hydrates that can be used at high temperature, discharging thermal energy into the atmosphere. And we more or less have the equilibrium data as well. We have also identified the growth mechanism of hydrate crystal, and we will have to understand more about the multi-phase dynamics. Now we have made a new hydrate. We need to do some physical property baseline. So with something like what Dr. Riepmeister does, or Dr. Alavi does. We need to do something like that. And also, slowly, commercial companies would come into the research and development. So we have to study more about how to design the whole system. And this is something that that could be worked together by Canada and Japan. As I mentioned, this is going to be a very complex, difficult technology. But once we achieve this, there is a good potential that we can achieve really high efficiency. So we want to maintain our challenging spirit in our research and development. Moving on to the next topic about thermal storage.
I'd like to talk about cool energy storage. This year, TEPCO has been releasing an electric power use forecast. You might have seen this kind of graph. During daytime, because of air conditioning demand, there is a peak demand for power. summertime, it's quite hot until evening. But during nighttime, one might turn off the air conditioning so that demand will go down. So there is extra room to supply electricity during nighttime. If the cool energy can be stored during nighttime, it can be used during daytime. So this is the cool energy storage-based air conditioning system. A peak demand shift is necessary to improve the power generation efficiency. This is clearly shown in the NEDO's technology strategy map, but going forward, the technology strategic map may be modified. The ice storage or water storage system can be efficiently utilized. Instead of ice-based cool energy storage, hydrate can be used. Why is it better to use hydrate? Because for air conditioning, low temperature needed is 5 to 12 degrees, but recently 15 degrees is enough. But for ice, the melting happens at decompose at 0 degree, which is too low. Cool energy storage may be sounding as a good technology, but there is something inefficient going on. For cooling energy storage, hydrate is better depending on the selection of a guest material. This is the cooling cycle is a reversible cycle. It is a reversed Carnot cycle. This is a very simple formula. If you set the high temperature heat source and low temperature heat source, that's enough. You can calculate the cooling unit efficiency. Ice is generated at 0 degrees, and around 27 degrees the heat is radiated. COP for ice is around 7. If you the storage temperature, if you replace the ice with hydrate, 10 degrees at centigrade, COP increased to 10, so 40% improvement. So this is the benefit of using hydrate. But are there any hydrate that can be formulated at 10 degrees? Yes, IHI and Keio University tried cyclopentan-based hydrate. It was not 10 degrees, it was generated at 7 degrees. Compared to water-based cooling unit, 15% less conversion rate. It requires agitation and other processes. This one used the active surfactant. If we made a immersion, it worked better. By using immersion, 93% of water was converted into hydrate. We have done this kind of research. Cyclopentan hydrate is worked on by IHI. 100 kiloliter level container is used, and dynamic heat conversion is possible, and storage temperature can be as low as 7 degrees, and cost calculation is being done by IHI. So depending on the material used for storage, this cyclopentan hydrate can be very efficient. Not only the residential air conditioning, but server room air conditioning is in demand as well. Since there are no people in the server room, the cool heat storage temperature can be 7 degrees. 15 to 20 degrees. This is an example of a PCM ceiling. On the ceiling, the PCM material used during daytime, it melts and it mildly cools the room. But the storage temperature can be higher in this setting. Maybe 20 degrees is sufficient according to a certain source. So hydrate with a varying temperature range needs to be identified. IH together with ITI, Keio University, and Takiya-san from AIST collaborated to discover a new hydrate. This one can be used for residential air conditioning. The equilibrium temperature is around 10 degrees. The Royal Society of Chemistry journal called RSC Advances had an article on this. And there's a hydrate that whose equilibrium temperature is 18 degrees. So this is applicable for server room air conditioning. What are the challenges going forward? If you discover different hydrates, there can be ones that are suitable for air conditioning, and we need hydrate that have wide-ranged equilibrium temperature. In the system engineering department, there is a group of people headed by Professor Nagashima, who has expertise in measuring the heat transfer. And within the Keio University, we have CO2 reduction group, and we're trying to get a fund from Environmental Ministry. It will be a 3-year project. And for the first time in Keio, hydrate-based cool energy storage project will be carried out with Ministry of Environmental Fund. Thank you.
Energy saving technology and thermal storage technology was the focus of this presentation. Does anybody have a question? If not, since we're pressed for time, we would like to move on to the last presentation of the afternoon session. Thank you very much indeed.